and since then worked on various topics. Some of them will be presented today, bosonic systems, and he also worked on error correction. You know, quantum computing of the future is practically impossible without error correction. So, and actually, before his talk, he sent us 4 topics that he potentially can talk today about. So we try to choose for everybody, something for everybody. But probably he will talk more about the topics that he has other presentations. Actually, if you go online, YouTube, he has a lot of lectures on other topics. So if you didn't see something that you would like to learn more in this talk, then welcome to go online and check more on his work. So please join me in welcoming Victor at University of Toronto.
Thanks, everybody. So I like to talk about today how to utilize more of Hilbert space that's available in experimental platforms. So the way I see a particular quantum system or any sort of quantum system is as follows. You can divide it into a number of subsystems that are in tensor product with each other. The number of subsystems is basically on this axis, and then each subsystem has some amount of energy levels. It's formally usually infinite, but people utilize only the first few lying energy levels, right? And what typically people do, and this is sort of the minimum non-trivial example, is they utilize the first 2 levels of any subsystem, and they call it a qubit or a spin 1/2. Then they stack a bunch of these together. And if in case, say, you want to do a quantum computer, you have to do error correction. So you have enough of these so that you can redundantly encode information in this large Hilbert space. And this is the paradigm of many different, very viable technologies. However, what is interesting to me and has been for a while is sort of utilizing the larger number of available energy levels per subsystem. Okay, and this also provides, in the case of, say, error correction, an extra layer of redundancy, right? It's a different type of infinity than the thermodynamic limit. It's sort of like an infinite photon limit, but there's nevertheless Hilbert space there that we can utilize. And there are basically kind of 2 major pushes to utilize for systems that are viable for being utilized in this way. Namely, one is the harmonic oscillator. Is just an abstract quantum system that describes 4 or 5, if you include free space, sort of quantum systems that are very naturally occurring in experimental labs and very controllable. And the second one is sort of what I was doing as a postdoc is another system that also has an infinite ladder of states, but it's very different. It's based on angular momentum, so you see these degeneracies, and that's rigid bodies. I think the door is closed. I'm not going to talk too much about rigid bodies, but I'm just saying this is sort of the overarching umbrella. And I'm happy to hear any questions, interruptions, feel free to. So the harmonic oscillator has some objects there that are analogs of qubit systems. And who's heard of harmonic oscillator, right? Like, okay, good. So I'm going to kind of not get into too much, but if you haven't, you can associate if you associate a qubit with a particle on a pizza, right? You can associate an oscillator with making the pizza slices very thin and popping open and making it infinite on a real line. Okay. And but in both cases, you have the eigenstate, the computational basis states. In this case, these are not technically states because they're not normalizable, but it doesn't matter. Dirac was totally right. This is the right notation, and these are the right things to use for some purposes. And there's a sort of analogs between concepts that occur on this side in the qubit case, and things that occur on this phase space side. So, for example, displacement operators. There's these things called Gaussian operations. If you don't know these last names, then on neither side, then it doesn't matter. So I'll just sort of brush through these, but if you're welcome to ask any questions if you want. So there's also, I'm sorry to also just throw this slide at you, but I guess this is just a shameless advertisement of this list that I made of use cases of infinite dimensional spaces in this review, brief tutorial. There's a few use cases, including, and many of them, I think 3 or 4 for quantum control and error correction occur because the Hilbert space is formally infinite. And so while you're not, there's theorems that no-go theorems that that you can't do this or you can't do that for finite dimensional systems that don't no longer apply for infinite dimensional systems. Okay, and there's several ones, including, like I said, one from there's some you can't amplify a Hamiltonian. This is Christian Arendt's quantum control. They proved you can't do it for finite dimensional, but then they use squeezing and they kind of amplify it for infinite dimensional. That one is not even on this slide, but it's in this review that I'm shamelessly advertising.
So one question here, there is, as you pointed out, there is a difference between infinite dimensional and finite dimensional. And with the qubit idea, you go to the finite dimensional, but not infinite. And with the bosonic, potentially you can go to the infinite dimensional, right?
It's already infinite dimensional. Even a coherent state,
right.
Something as simple as that is using the infinite dimensional space. It has this exponential tail, but it's using it, and it's important because you can do things with those states because of that.
So your talk will be about like essentially using dimensional Hilbert space.
Different tools for porting different tools from finite to infinite.
Okay.
Yeah.
Sure.
Yeah.
So just to follow up this, the infinite dimension is necessarily continuous.
What is continuous?
The infinite dimension.
Doesn't
Like you contrasted finite in the discrete case.
yes.
And that is finite dimension. And contrasted it with the infinite dimension.
I got you. Countable. Every one of these systems that I'm going to talk about has a countably infinite basis. That's called a separable Hilbert space, not to be confused with separable state. It's a weird name.
You can decompose there.
Yes.
In that space.
Every one of these has a countably infinite basis. So in the mathematical sense, the rigid body space and the harmonic oscillator space are isomorphic. But when somebody says that to me, I get annoyed because the physics of those spaces are very different, right? They both have a countable basis, countably infinite. Now, these other position eigenstates that I mentioned, those are these Dirac non-normalizable states. Those can be parametrized by a continuous variable like position, right? But you can always just go back to normal math and just define a normal countably infinite basis for all these spaces. Sometimes from the physics perspective, you want to use other bases, but you're always going to be able to do this. So one of the things I want to relay here is infinite dimensional designs. Who knows what a design or a quadrature or a cubature is? Okay. So basically, the overarching idea of designs is to reduce integrals of certain stuff over hard spaces to integrals or sums over that same certain stuff over easy spaces. And depending on the stuff, if it's certain stuff, this is an equality. And I think this is amazing. How are you able to discretize an integral and still get it exactly right? When we define integrals, we discretize them, but it's only right in the limit that the discretization is very small. Here, you have this exact discretization, and it gives you the exact value of the integral. However, this doesn't work for all stuff. It has to be certain stuff, okay? For example, let's consider the space to be just this orange triangle. And let's just denote the thing we're going to sum over as these 3 points. And it turns out that the integral over this triangle of these functions is equal to the sum over these 3 points. Now, which functions does this work for? It works for degree 2 polynomials on the triangle. So this is a 2 design because the strength is 2, namely the equality holds for degree 2 polynomials. And this is a 2 design on the triangle. Okay.
Because the somewhat simpler example would be Newton-Cotes quadratures, right? So where for integrating linear function, you need just 2 points. quadratic one in one.
Oh, yeah, that's even better. Yeah.
Well, but
Yeah,
of
yeah.
course it doesn't have a fancy design name.
It's called a quadrature. Yeah, well, here's some history. This should also be this is not the earliest reference. This is just a book. So I'm sorry about that. But these are spherical. There's spherical designs, of course, like this goes back to Gauss. These are quadratures. These are just, so sorry, what am I saying? These are designs on different spaces, X. Okay. If X is the real, space, these are called quadratures or cubatures in some cases, used a lot in numerical analysis and quantum chemistry. If it's a sphere, real or complex, these are called spherical designs. If the space is the unitary group, which you can also think of as a space, that's what's cool about Lie groups, then this is a unitary design. Okay, and these are quantum state designs, because this is the formal name for what the space of quantum states is, complex projective plane. Because you have to normalize and then you have to remove global phase, so you get this projective thing. Okay, and there's a lot of different applications, including right now in quantum, people are very much using unitary designs to prove that certain techniques work a lot better than you may have expected. So what is the sort of the intuition behind why these are useful? Let's consider state design. So we're specializing to all quantum states. You can integrate over all quantum states, it turns out, not too bad. And so what happens? So let's consider a polynomial in the amplitudes of a quantum state. So these are our values. This is our x, y, z, w, and we have a function that's a degree 2 polynomial in all of these different variables. There's a lot of variables because you have a d-dimensional quantum state. And what happens now? So how does this work? So if you average over a design, this is just the statistics version of capital sigma. So what did I? Right, so this is a polynomial in all of these variables, and these are its coefficients. Now, it turns out that you can express this as an expectation value over 2 copies of the state with some operator corresponding to f hat. And this f hat is just the coefficients, a matrix of the coefficients, or tensor of the coefficients, I guess. No, a matrix. And then the size just get collected into these 2 copies. And now, now you can use the design formula, and you can show that the average over the design, if it is indeed a 2 design, then this is equal to the average over all pure states, which then you can go back and unpack this back into the function, and you see that the average is over the function of the pure state. So this is how you encode functions into Hilbert space. You can encode them as operators. And evaluations of functions are expectation values of corresponding operators and copies of the states. If this is a degree 3 polynomial, then you have 3 copies of the states. Okay, this is one of those things that people don't write. So I'm hoping this is helping. So you can map functions of variables into observables, evaluated in different numbers of copies. Okay, so so for state and unitary designs, this is the previous work. There was a paper that proved sort of everything has can have a design. And what we do is we look at infinite dimensional spaces. So these are all for finite dimensional spaces, fixed numbers of qubits and qubits, and we look at this infinite dimensional space. Previously there was this paper actually this was presented in Toronto at the CQIIC seminar. That's when I first heard about it, by Robin. No, I think it was Peter, maybe. Anyway, I was here at that time and I heard about it and I was totally confused. I don't know what was going on. And finally, it took me 13 years to get back to it. They showed that actually, if you use sort of a set of easy states, you do not have designs other than 1 designs, which are just bases for infinite dimensional spaces. And we show that you can't actually have designs at all for even if you use harder states other than these Gaussian states.
So
yeah,
the problem that you are addressing here is to constructing designs for this
infinite dimensional space.
Yeah, which was done before.
Which was not done before. There was a no-go theorem showing that if you use these types of states to construct designs, you can't get past just 1 designs.
And
yeah,
you avoided this no-go statement by changing something.
Well, hang tight.
Okay.
Yeah.
The difference between using general finite versus countable and Hilbert space, or is it exactly?
Well, the Hilbert space is the same for every row. So you fix a Hilbert space, and then you look at which states to use for that Hilbert space. There's certain subsets of easy states, and then there's like just your general states. And the easy states and easy unitaries are operations and states that are sort of some distinguished set. Here it's called Clifford, here it's called Gaussian. And yeah.
Can you clarify what Gaussian unitaries
are? Sure, it's things that can be written as exponentials of, or products of exponentials of things that are quadratic in the positions and the momenta of your oscillators, right? Products, non-compact group. You can't just write it as one exponential. I made that mistake in teaching in class and a mathematician corrected me. Okay. So what goes wrong for this infinite dimensional case? Well, it turns out that the normalization is the problem. You need to basically have states like this. You need to have sort of even superpositions of states of your basis states here to form a design, to be part of a design. You need to include that part of the space, which is this sort of in even superposition. And for a d-dimensional space, if you normalize this, this disappears. This goes to 0. So the state, a normalized superposition of a countably infinite number of states just doesn't exist, right? So that's bad. Why is this bad? Because these states are needed, and they are needed because they, if you write them as density matrices, the populations of a density matrix, remember they have to add up to 1. They form what's called a simplex. It's this notion of for 2 dimensions, it's like a line. For 3, it's like a triangle. For 4, it's like a tetrahedron. Okay. So basically, when you want to design a design on states, you have to also worry about a design on this simplex. You can divide every state into probabilities and phases. The probabilities form a simplex, the phases form a torus. And if you have a design on your full state space, you're going to have one on the simplex. Conversely, if you don't have a design, if it's impossible to do a design on a particular simplex, you won't have a state design. And what we have here is an infinite dimensional simplex. Because when d goes to infinity, we have this, infinite dimensional version of an equilateral triangle or tetrahedron, so to say.
Is it a sphere or something?
No, it's a valid thing. It's an infinite dimensional simplex. It's not a sphere. I can't visualize it either. But what I want to just come across here is that this point is very important in the simplex, and it's actually sort of a point like at the center or around the center is necessary for you to have a simplex design. Every simplex design has some point close to the center. But the point is that these types of points, they disappear from the simplex when you go to infinite dimensions. And when you have no point like this that you can use, you can't have any simplex design. And because you don't have any simplex designs, you don't have any state designs. And then by contradiction, you can also show that, well, if you don't have any state, if you had a state design, you would have been, sorry, if you had a unitary design, you could always make a state design. So conversely, if you have no state design, then you can't have a unitary design. So nothing works, everything is broken. Okay. So the simple idea that my student thought of is just, well, why don't we just remove the normalization constraint? And let's allow ourselves to use non-normalizable states. And those position eigenstates that I mentioned that everybody knows and loves, those are also an example of non-normalizable states. They're perfectly fine to deal with if you just have to remember the Dirac delta function, okay? So those are types of states that are experimentally also relevant. There's other types of states that you may or may not have heard that are also these types of non-normalizable states, but are also useful and interesting. And then it turns out that if we relax the normalization constraint, allow us to use non-normalizable states designs out of these states exist. Okay. So here is one example that we found. We did not find many examples, but we did find one. And these are the ingredients for this set of non-normalizable states. We can call them vectors. Are the Fock states, so literally the basis that you have for your space. And then these things called phase states, which are equal superpositions of all Fock states with a phase theta here. that's an angle. And then you introduce an additional parameter that is this phi parameter that now is multiplied by n squared. Okay, and together these form a rigged 2 design. Now these are not normalizable, these are, and we have to use both. So what is happening here? Well, if you remember our simplex picture, you can think of this triangle. To make a design on a simplex, you sort of need to cover the edges of the triangle and something in the center. These are the edges. These are all the corners of our infinite dimensional equilateral triangle. And these are points inside the simplex. The one with theta phi equals 0 is this non-normalizable centroid. See, I didn't normalize it. And then for the phases, remember, we also have phases in our quantum states. We do this theta phi twirling or averaging, and that covers all the phases. Okay, so this is sort of an intuition of why this works. So armed with these designs, we can apply them to show that certain protocols from the discrete variable case can be generalized to the infinite dimensional case. Here's one protocol or relation where designs have been utilized in the discrete case. State designs for qubits or finite dimensional system allow for a relation between 2 different notions of distances between states or fidelities. So if you have a quantum channel, so these are the 2 fidelities. This is what's called the average fidelity. You send a state through a channel and you look at what happened to it, how far it went from its initial from the initial state, and then you do this over all possible states. This is called the entanglement fidelity. You send half, you have an entangled state or some sort of state, you send half of it through the channel, and then you look at what happened there. And you do that for a specific state called a maximally entangled state. So these fidelities may not look related, but they are. They're actually sort of proportional to one another. And the way you prove that is you use designs. Remember, we had functions of amplitudes being translated into expectation values with multiple copies. Well, here are the multiple copies. You can see them already. It's 2 copies. So you just need a 2 design. You do the 2 design thing, and then you can get to this one. Okay. And we can do the same thing. For this case, so you can sort of softly normalize these things because otherwise, right? So let us normalize these things a little bit because there is already a notion of entanglement fidelity for continuous variable systems that utilize a state that is sort of maximally entangled called a 2-mode squeeze state. And at infinite squeezing, this becomes an analog of this one, but it's not normalizable. So people sort of soften it, make it have a regularized sort of tail by introducing finite squeezing. And so this is something that's existed, and now we can introduce this quantity because we have a design. We can do this average, and we insert these things to match the beta here, and we get a relation that's very similar to this, except now there's an effective dimension that's not an integer that is dependent on the sort of the amount of squeezing you have in this 2-mode squeeze state. Has anyone seen this before? Okay. Now, another tool a more recent tool that people have been utilizing in discrete variable systems, whose properties are proven using designs, is a state tomography protocol called classical shadows. And here I will just sort of spell it out a little bit, is that if you have a quantum state, you're not going to be able to store the state perfectly because this state has an exponential number of coefficients in a multi-qubit space, right? Exponential in the number of qubits. There's a lot of different state amplitudes here. You're gonna run out of room to store it as n increases. So what you do is you cook up different snapshots of the state and such that each snapshot you can store on the computer. It's not going to blow up. The amount of storage space is not going to blow up. And in these snapshots, in this case, they're called shadows. Generally, they're called estimators. And if you have enough of these estimators, you can roughly know the state. And one of the ways to show that is that on average, the estimators better give you the state. Right? You have to show that at least if you get enough of these, they're going to get, if you use all of them, then you're going to get exactly the state. That's one of the things you have to show. And you also then have to show that you don't need too many of them to approximate the state well, right? It's like a law of large numbers. First, you show that the average, is 50% if you're flipping heads or tails, right? But then you have to show that the variance is actually something that's not very large. And those are two things you got to show for sort of this classical shadows protocol. And this was shown using designs. And what are these shadows? Well, these shadows are just particular quantum. They're not even states. They're not even trace preserving. And but nevertheless, this statistics here works, which I think is amazing. They're not physical states, but if you take enough of them, you can get a physical state back out. I thought that was beautiful. And these are obtained by measuring each qubit in one of three ways: 0, 1 basis, plus minus I basis. You're picking which one you do randomly, flipping a three-sided coin and picking which one, and then obtaining a bit outcome. So each of these S's is a trit and a bit, which measurement you randomly picked, and the outcome. Yeah.
Why do you say that they're not physical states, the ones that you obtain, I guess,
Because
in the measure?
Oh, in the measurement, if you're doing the measurement, yes, it's that you get in a physical state. But what you plug in for the shadow is not, because of this minus I and the 3.
Okay. Okay. So
Yeah.
it's like computational.
Yeah. So in this case, you have this shadow, and it turns out that as weird as these look, you can show that they do give you the state. So what do we have on the other side? So and these are designs. These are state designs. This is for a single qubit. These are points on the octahedron of the block sphere, and these form a 3 design. It's 3 state design. Well, what do we have? We have a 2 design. So we could at least get something out. Turns out our 2 design that I showed you with the Fock states and the phase states, using these now as the snapshots for the state and measuring either in the Fock basis or in the phase state basis for a chosen theta, gives you a CV version of this protocol, a very similar one visually with similar guarantees. Yeah.
Like you said, it's countable state, it's also countable states, but find that they are like essentially continuous.
Correct.
Right. So like how are they countable?
These are not countable. I'm saying each space admits a countable basis. Each of these can be expressed in said countable basis, but a design is a set of states that's larger than a basis. It needs more than that. Bases are 1 designs, because all they do is resolve the identity on 1 copy of the space. But to resolve the appropriate thing on 2 and 3 and 4 copies, you need something more than a basis. And there's bounds on the number of points you need in any space for a particular T design. Okay, and so that's why there's quite a bit of states here, right? Like each of these, for a fixed theta, each of these resolves the identity as well. So we have a continuum of bases here, parameterized by theta, plus another discrete one that's the original one for the Fock states, coming from the Fock states.
Talk more about what is the shadow?
Yes, a shadow.
It's like a projection, but the question is on what?
So yeah. So it's a projection on a particular direction in the block sphere. So for this qubit case, you have this block sphere, and you pick which way to project: z-axis, x-axis, y-axis. And these are the 2 projections you get for the 3 respective cases. Okay, so we've seen the applications of designs. I'm going to pivot a little bit, and I'm going to reiterate or evolve a little bit the conversation about these shadows. What was so nice about these shadows? You were allowed to average them to get a state, which is something hard, using something very easy. What if we apply that type of thinking frame of mind to already established tomography protocols from quantum optics? Do these work well? Right? Do these conventional protocols work as well as the shadows do? These are not based on designs anymore. These are based on some other complicated things from quantum optics. But can we reframe them as shadows, and can we use the type of sort of variance, mean and variance calculations that we did for shadows to prove similar properties about these other protocols? Turns out that in some cases, in many cases, yes. So here's how the physicist thinks, right? So you can expand a density matrix in various different quantum optics ways. Not physicist, quantum optician. You remember this from your quantum optics class: P representation, Q representation, Wigner function, Fock basis, this basis, that basis, a bazillion different ways, right? Okay, and each one is basically just a sum over some space, some set of parameters over some states, or not even states, some objects, whatever they are, displacements, whatever, with some coefficients. It's kind of like a basis expansion, but for an operator. Now, if these coefficients can be interpreted as probabilities, namely, if they are between 0 and 1, they can be made to be between 0 and 1, which means that they have to sum up to 1, and they all have to be greater than 0. Then we can now go to the statistics department and pretend that these are samplers or estimators of a quantity, and they are averaged over the whole set of estimators to get the quantity. Okay, this is not just a different way of writing things, this is a different way of thinking to me. Okay, this E, this integral, this capital sigma is all the same, but in physics you don't think of this statistically. But now when you're thinking in the statistical way, you can say, well, what if we only sample a part of the space? What do we get? Well, it turns out that you can work with these in the same way. You sample capital T of them, and you're going to get something that approximates the state. And then you have to show, just like the shadows, and then you have to show that, okay, first of all, does this give you the exact state when T goes to infinity? Well, yes, that's clearly this. So the mean is the right thing. And then how quickly with increasing T does this give you the state to some given accuracy? And that's when that's the sort of the meat of this paper. And what do we get for example, homodyne shadows? Sorry, this should just be homodyne tomography, where now you can interpret each of these things as sort of the shadow. This pattern function, this is a crazy thing. Don't worry about it. That's the shadow. And luckily, these are coefficients that are clearly probabilities. And now we can cook up this sort of estimator that we can frame as a homodyne shadow. And with high probability, the number of samples required to estimate the state with the dimension of number of photons in the space scales polynomially as n to the 5th. And 1 over the square of the accuracy of the estimate. Okay, so this is just throwing statistics at the problem and showing that homodyne works this way if you do it. Yeah.
So just to get an intuition of the idea here, so suppose that you are tomographically reconstructing a coherent state.
Yes.
So what does the shadow look like for that?
The shadow would be the coherent state determines which one of these you get when you sample the coherent state, but they all will look the same. They're all independent of the state. They're these pattern functions, just like before when you had 0, 1, plus, minus. Those are all independent of the state, but which ones you get is determined by the state, by this overlap. So that's what's interesting, right? All these shadows are kind of the same object, independent of independent of the state. They all look the same, but which sum you get, which outcomes you get, which which thetas you get is determined by the outcome of your measurement, which is determined by the state. Okay, and there's another instance here. If we have photon number resolving detectors, You can also have an expansion like this. I mean, yeah, this is a generalized version of the P representation. For certain value, this representation is parameterized by R, something that goes, I think, from 1 to -1. For certain values of R, for say R equals 0, you can reinterpret it as shadows. These are positive numbers, and the number of samples now scales is roughly under the 4th. Okay. So statistics really help. Yeah. This is if you have some photon number resolving detectors.
And what are you trying to, what's the question? Are you trying to answer?
Again, you're trying to figure out what state you have in your photonic system. And you're performing some measurements to figure out the state. And this is an efficient way to do that using not too many samples, depending on the size of your state. This is still a state tomography protocol. And it doesn't work for all R. Yeah.
Why not just use like protection of the protocol?
No, it's a good question. It's a similar question as why can't you just use a basis as a design? Well, you need more than just a basis. What you're saying is this orthonormal basis construction, and you sort of like each one is kind of taking like a cross section, which gives you the whole state if you have them all, but the variance might not be very convergent. For a good sort of expansion, you kind of need many different directions that you can sample them all at the same time, and in that way you can estimate the state with a small number of samples.
So like if I have a single photon, like for a whole number of detector, like it would like give us state, you'll see like there is one photon complete example, like approximations of. But like for here, if you use these operators, how would you interpret the thing? Like how would you interpret this? Like,
Yeah, sorry, I see. This is not just photon resolving detectors. This is also doing something with coherent states. These are just displaced coherent states. So the N here is for the photon number resolving, but then there's some displacement. You do some interference with some local oscillator, and then you do PNR. I don't remember the details of the protocol, but this is a very established protocol. There's a figure in our paper, but yeah, it's more than just PNR. Okay, so now that was state tomography. We were trying to figure out what is in our system, and now we want to protect information stored in our system. Let's go to error correction. And the goal of error correction is to preserve messages sent through a noisy transmission channel by encoding the messages redundantly in what's called an error correcting encoding or an error correcting code. The noisy transmission channel can be time or space. And the whole sketch of this very general theory started by Shannon goes as follows. You have a message, you encode it using some map called an encoder. You send it through your channel, which will impart some noise that you're not able to control. The channel can be just stationary in space and you're just storing in time, or it can be traveling in time like in an optical fiber. Then at the other end, you try to extract the information using a map called a decoder. And the whole point of this is that this whole situation has to roughly equal rho. You can just delete DE here. For simplicity, this should be equal to something that was basically as if you had never done this and you had just given the message to the other side that was in a perfect way. So this paradigm is in play anytime you talk on your cell phone, you Netflix and chill. Anytime you want to communicate with satellites, these redundant encodings are used here for classical information every day, hard drives. And of course, they're useful for us in the quantum realm for communicating quantum information or storing it in said devices. So let's go now to bosonic systems. I told you they offer an extra degree of redundancy that you can try to utilize for designing good error-corrected encodings. And bosonic systems for a single mode, you can draw them in phase space, position and momentum, or I and Q. And the types of different encodings that have been developed over the past 20 some odd years can be characterized in sort of either Cartesian coordinates or polar coordinates. Easy, right? So there's two basic classes of codes. There are codes where you can think of them as superpositions of coherent states on a lattice or on a circle. And there's classical versions of these. So when they send information through electromagnetic fibers, they can encode in some ice cream scoop of this lattice or just encode on the circle for fixed energy transmission. These are called quadrature amplitude modulation and phase shift key rings in the classical world. But then if we take superpositions of them, we can design quantum codes. Well, what about the multimode picture? Well, now we have this, 2 dimensions per mode. So we have this, 2 n-dimensional phase space for n modes. Well, what do we do there? Well, it turns out these are not very well explored. And while single mode things are here, so normal qubit codes are here, single mode codes that I've just described are all the way over here. They're only utilizing one photonic or microwave system. And multi-mode codes would be over here, but this is very much sort of, here there be demons. And we don't know too much about this. And we can try to cook up different combinations of these codes, there are worthwhile goals that we would be trying to achieve in trying to do this. So instead of, there's combinations of already known codes that you can do, and people and companies are actively exploring these for blueprints of quantum computers. But there may be some intrinsically bosonic, intrinsically continuous variable codes that lie on multiple modes that might be useful and help us overcome some of the difficulties that these conventional combination schemes or concatenation schemes have. Okay. So we have sort of things in both these directions. Let me tell you the thing I'm most excited about is generalizing this. So, and in retrospect, this is dead obvious. How do you generalize a circle to multiple dimensions? So this is a single mode bosonic code. And now we want to generalize these types of rotation-based codes to multiple dimensions. Now we have a 2 n-dimensional phase space. What's the generalization of a circle in multiple dimensions? The sphere. That's it. I was thinking about this since grad school. You could try. No, I mean, I think a torus is a subset of a sphere in high dimensions. Like here is a 1 torus, and a 3 sphere, the 2 torus. I think they are, but like the 3 sphere, there's 2 phases, alpha and gamma. Those form a torus. And I don't understand where that torus is because I can't visualize it, but I think it's in there.
Sphere is like one equation for squares equals to 1, let's say.
Yeah.
Torus is for each.
Yeah, you solve the equations and you get parameters, Euler angles, alpha, beta, gamma. For a fixed beta that's not 0 or pi, you have alpha and gamma. That's a torus. Alpha and gamma are 2 angles. That's a torus. I'm not saying I understand it, but I'm saying it's in there. So in some sense, we're general. But yes, you can try to do torus. You're right. We did sphere.
No, I meant to say like torus has like different rating numbers than sphere.
Yeah, I know it's topologically different, but I'm just saying parameter-wise, it's in there. Like if you, oh yeah, this is 2 sphere. You restrict to the equator, you can have flux through this thing, right? If you restrict it to the equator, you get a totally different system. You get a ring, and you can have flux through the ring. But if you now open it up to the sphere, the flux is not topologically relevant anymore. So it's in there if you restrict to it. You can even see it through the Earth, right? 2 sphere. You have to restrict to it, though. I agree. Then you get the different Chern number and everything.
So just to be clear, your point is that the multidimensional sphere is less restricted than multidimensional torus, and that's why torus would be surpassed by the multidimensional sphere.
I guess in principle, yeah, if we restrict ourselves to the equator of a 2 sphere, we get a 1 torus. But I'm not saying we did that. We don't know any, we didn't really restrict to the torus. We try to use the full sphere. The point is you want to use the redundancy as best as maximally as possible. And if we have a sphere at our disposal, you want to use the whole thing. However, yes, you can take a single mode code like this and embed it into a great circle in a higher dimensional sphere. Always, no problem. But then you're not utilizing the rest of the sphere. And why not use the full phase space? Well, in that case, then you go back to kind of lattices. Then the lattices are the best thing. But if you restrict a fixed energy, fixed total number of photons, then you're on a sphere. So the prominent representative of codes on a circle for a single mode are called the cat codes. Who's heard of the cat codes? There's a ton of work that's been realized over them in the past 10 years for quantum computing. Right, whenever I underline something, this is an experiment. And in fact, this was the first experiment that actually allowed you to utilize error correction in a way that preserved the message. In quantum computing, it's such a sort of a beginning endeavor that error correction doesn't actually work because of all the complications of the hardware yet. And people are still working very hard to make sure that they can implement error correction protocols in a way that they actually work. And the first one to do so, the first one that actually maintained the system at a rate that would have been the same as if they had not done this redundant encoding and all this overhead, was the cat code. This is called break even, that they basically were maintaining it at the same lifetime as the lifetime that you would have had if you did not encode it and you'd reuse the redundant space. Since then, they've gone beyond break even, but that was done using lattices. So spheres were used for break even. All right, and that's the take-home message for these spherical codes. For a cat code, a code is a two-dimensional or higher dimensional subspace of your system that you're using to store quantum information. So you have this big, large space, and you're trying to store a smaller space in it, and you try to cleverly choose a subspace such that that information can be recovered after errors. And that's the whole art of quantum error correction. The subspace here, which can be defined using a basis, is just superpositions of coherent states. So here, the subspace is spanned by one cat state, which is alpha plus minus alpha for some radius alpha. Let's fix it to be 1. And the logical 1, the other basis state for the code space, is spanned by I alpha and minus I alpha. Okay. So they're like this. I can get into why what is the benefits that code offers, what kind of noise it protects from. If you'd like, feel free to ask me. I will though continue just with this geometric picture just to convey how to generalize it. And these states form a line segment, vertices of a line segment. So do these together, the two code words or logical basis states form a square. Then if you use now 3 states per code word, you get 2 triangles, and this whole set of 6 equidistant states on a circle form a hexagon, vertices of a hexagon. And this is the simple generalizations. You can do this for higher dimensional spheres. If you pick now 2 tetrahedra for the 2 respective code words, then you have forming them, they form a cube. If you pick 5 tetrahedra, they form the vertices of a dodecahedron. And then you can just go crazy because you have multiple modes to pick from, right? And that's what's interesting, because having multiple modes opens you up to the possibility of constructing very cute, exotic, beautiful polytopes in the space of coherent states of fixed energy. Now, maybe I'll tell you why these codes are useful. So mathematically, each code word is an equal superposition of points in a constellation, C0 and C1. I told you the constellation here was just a line segment, alpha minus alpha, and here I alpha minus I alpha. Now, what do these codes protect against, and how much time do I have? Oh, cool. Am I going too fast? Feel free to stop me and ask any questions.
Are these alpha?
Yes. Yeah. So what do these codes protect against? What is the noise that we're trying to fight here with these codes? Well, one set of noise is dephasing, angular diffusion, random rotations applied to your state that'll rotate your square like this. And what protects us against this? Well, the points are separated from each other, and for each sort of protection, you have to quantify how well separated they are. And you can quantify it by fixing alpha to be 1 for convention and just looking at the minimal distance between 2 points. And that's called, I'll call it the resolution, because if remember coherent states, the closer they are, the worse you can resolve them. The farther they are, the better you can resolve them. So this distance for fixed radius quantifies how well you can resolve them at alpha equal to 1. And so this protects against random rotations. And the protection is quantified by this resolution. In this case, it's 2. Squaring it because the numbers are prettier. And you would maybe think we're done. And if this was indeed the only noise source, then we could, why don't we just pick one state to be, the red one just to be here and the blue one to be here? Why do we need superpositions at all in the first place? You're maybe wondering. Well, if rotations were the only noise source, we would not need superpositions. We could just store one here and one here, and they would be antipodal, and the resolution between them would be 4, which is the highest resolution you can have. However, that's not the only noise source that we're fighting against. In quantum mechanics, there's always 2 noise sources because we're storing quantum information. There's noise sources that can exchange your states, and there's noise sources that cause relative phases between them to change, called phase errors. We always have to worry about phase errors because we're storing quantum information. If we were storing classical information, we wouldn't have to worry about phase errors because classical information is not in a quantum superposition. So what's the second source of noise? Second source of noise is amplitude damping, photon loss, leakage of photons out of your cavity, out of your fiber, attenuation, whatever you name, it's the same mathematical thing. So that's why we need superpositions, because photon loss is a source of phase errors for these codes. So how do we see that? Well, we remember the famous property of coherent states. They're right eigenstates of what? Annihilation operator. So when you apply an annihilation operator onto our cat states, it's going to spit out the value of the coherent state next to the coefficient. And when we do, and so this photon loss operator, you can think of as acting as inducing a potential on the sphere. Okay. And you can think of it as a bad environment trying to sniff out what your logical information is by inducing a potential and seeing whether that potential can distinguish the 2 different code words, logical 0 and logical 1. So we have to look at what are the averages of that potential over the points in the constellation. This is where multiple points matter, because if the points are not uniformly distributed, then the environment will be able to cook up a potential that can sniff out, this one's at the North Pole, this one's at the South Pole. But if the points are more uniform for each code word, then averaging them over the potential won't distinguish them because the averages will be the same. The environment won't be able to sniff out through some potential. Okay, and this is why you need multiple superpositions. This is why you need not only well-separated points, but also uniformly distributed points. And that's where now we start to distribute them. At least here, this is the least we can do. We can just add another one antipodally. And when we do that, this you can show that this corrects 1 photon loss or 1 photon gain. Yes. You didn't understand why what? So the reason you can think of it as a potential is because of this formula. So when you average, so when you look at what happens in a constellation up to some normalization stuff, this is average of points over the constellation, a function of the constellation averaged over the constellation. And you can think of this alpha as a potential function. More generally, you have products of loss operators, A, B, A dagger, B dagger, and this will induce a polynomial or a monomial on the space of states on the sphere. In this case, just on these 4 points, because that's the code. But in general, this is a monomial lying on the whole sphere, and it's trying to sniff out whether you're here or there. So these averages over the 2 constellations better be equal, otherwise the potential will distinguish them. And that's why you need uniform points as well separated. And of course, there's a tension between that, because the more uniform the distribution of points, the more points there are, and the less the distance is between them. And there's always this tension in all of error correction between the 2 sources of noise. The better you protect against one, the worse you are at the other. And here, if you put more points, you can protect against more losses, more gains, but then you'll lose your resolution, and vice versa. And so cat codes, what do? Well, they just tune how many points. You have an n-gon or p-gon for general cat codes, which protects against p losses, but the resolution scales as 1 over p squared, because the resolution is sine squared 2 pi over p or something. And then, yeah, you can do gates and operations here that I don't know if I want to get into. You're welcome to ask me. Yeah. So how do we extend this to multiple dimensions? Here's a simple example of a 2-mode code. So now we have 2-mode coherent states. Each one is a complex number. And so the constellation here for fixed radius is parameterized by these 2-dimensional complex vectors, with omega being a 5th root of unity. And these form your generalizations of the equilateral triangle that I mentioned, called the simplex. This is called a 5-cell, which is a simplex in 4 dimensions. The notion of a simplex is that in this, what's relevant here is that the distances between any pair of points are the same. That's what defines a simplex. And the 2D version is the equilateral triangle, and you saw that already. So what do these protect against? Well, these aren't too good. These aren't that good. The resolution is lower than that of a cat code with 4 components. So a stop sign. However, it detects more loss operators than the 4-component cat code, but it only corrects 1 loss. And there's some logicals and stabilizers. Now, what I want to highlight here is that simplices exist in all dimensions, as we've already seen. So we can go off and create an infinite family of simplex codes, so these do get a little better, because you're packing more, you're packing in a higher dimensional sphere. The points are in some sense like get better and better distributed, and you approach the resolution decreases to a constant that is the same as the 4-cat, but now it can detect then it can detect 1 more loss and correct the same amount. So this red part goes away asymptotically with the number of modes. An example of how you can pack higher dimensions and get better parameters at the expense of using more dimensions, of course. And we can go nuts. So we have this beautiful Hessian polytope in 3 modes. So now we have a cube root of unity, and we have, these are its coordinates. We use a Hessian for the logical 0. It's 27 points, and we use the inverse of it, the one that's like reflected through the origin for logical 1, another 27 points. So physically, it's going to be harder to make a 27 3-mode cat state than a 2-mode, or than a single mode 2-component cat state. But the point is that the resources are the same type of resources. What do you gain though? Well, check it out. So the resolution is the same as that of a 6-component cat. Okay, but this detects as many losses as an 18-component cat and corrects as many losses as an 8-component cat. So if you fix the resolution and you look at a cat code with the same resolution, this code will outperform the cat code, detecting 5 more losses than the cat code and detecting 6 more losses than this cat code and correcting 1 more loss. And maybe I can go back to this after I cover this slide, but probably not. What is interesting about these quantum spherical codes is that we can also reinterpret code combinations of discrete variable and continuous variable code that already exist in the literature through this lens of high-dimensional hyperspherical codes. This is a paper by Amazon. They are trying to use a design that concatenates one of the best codes from the single mode case with one of the best ones from the multi-qubit case. Here, they encode each physical qubit already in a cat code with two components. So alpha and minus alpha are the two logical states. Sorry, one component. Right? Each logical state gets one component. This does not have protection against loss, but it does have protection against rotations. The best protection, in fact, for all the cat codes. And then they use those as your physical qubits. And they stack a bunch of them together. And then they encode again in a redundant way using these as physical qubits of an underlying surface code or toric code architecture. Who's heard of the surface or toric code? And this is just some multi-qubit code, but now each qubit is itself embedded in a bosonic mode. So this is a concatenation or combination of codes. And this is their blueprint for a future, hopefully future quantum computer that is based off of these two types of codes. Now we can interpret these codes and get many more operations. I guess I didn't really get into, but from our perspective, the code can be interpreted as follows. Each physical qubit basis state is labeled by a binary string, right? Each qubit is either 0 or 1. And what happens when you combine with cat codes is that you map this binary string to a vector via this antipodal mapping. 0 goes to alpha and 1 goes to minus alpha. And this is what happens. And you can do this antipodal mapping to any CSS code. This is a large family of qubit-based error correcting codes that include the surface code, but also many, many other codes. And applying this thinking of this concatenation this way, you can show that you can detect certain potentials on the sphere using the properties of the original CSS code when you embed it in the continuous variable bosonic space this way. So the CSS codes comes with its own distances, the number of Pauli X errors that can be detected, or the number of Pauli Z errors that can be detected. It comes with these two distances, and these two distances via this antipodal mapping translate to a resolution and a number that quantifies which monomials are correctable by the multimode cat code. So the Z distance gives you a how many monomials in the loss and gain operators you can detect. Namely, you can detect them on as many modes as the distance. And then the dx distance gives you a resolution, the distance between the coherent states. Why? Because the Hamming distance between the binary strings, the number of different elements the two binary strings have, naturally translates to the Euclidean distance between the coherent states. It's like a 3-line proof. Okay. And then there's gates and operations that we can use that actually people had not thought of before because they were not interpreting things this way. This might be useful for the Amazon people. Right, so now I'll just, yeah, we have some stuff on lattices. So I've mentioned concatenation. There are many other bosonic codes that people have been sort of introducing and studying. And so with sort of every new single mode bosonic code, you get another opportunity to combine it with a multi-qubit code and play these games where you combine different codes and you see what happens. Are they better or are they worse than the original, more conventional concatenation schemes? So there was a series of new codes that people had put out, namely these codes called GKP stabilizer codes that protect not a finite dimensional logical qubit or qubit, but an infinite dimensional logical mode against errors. And these codes were very interesting in that people had thought it might not be very possible to do that, but nevertheless, this paper proved that you can. And we tried to analyze these codes from the perspective of storing discrete information. So the concatenation would basically be taking multiple modes and encoding a logical mode in these multiple modes using this GKP stabilizer prescription. This is an infinite dimensional information space that's embedded redundantly in these multiple infinite dimensional ones, but then concatenating that by encoding a finite dimensional subspace in this infinite dimensional space. So this is the combination. More conventional schemes like the surface code I mentioned encode a logical qubit into surface code physical qubits, and then each physical qubit you encode in the cat code, for example. So you see the way you do this is very different. Here, the intermediate part is just the finite discrete variables, and here it's a continuous variable. And we were just trying to compare numerically and analytically which encoding was the best. And I would say that turns out for most cases the original encoding is better. That was a bit surprising. What?
No, really.
Yeah. So this is the communication application I didn't have time to do. So I want to say that want to highlight or advertise the University of Maryland. There's a lot of quantum centers there. If there's somebody there, or if there's something you're interested in, there's probably somebody there you can chat with. It's a very active place. Here are the centers. I work for NIST, and NIST has 2 centers that they collaborate within Maryland. The quantum state designs was done by Joe, graduate student, and Kunal, a postdoc now at IBM. Srilika was in charge of the shadow tomography. These quantum spherical codes was done by this team. And the decoding formalism I briefly mentioned is here. And then the communication aspect was done by Eric Kulf and with Tomasz Witek as well. So with that, I want to thank you for your attention.